I'm ready.
We're here to crack the solar system open like an egg. We're building a multi-injection kinetic accelerator for taking large stuff to extremely high speeds and putting it directly into orbit.
Hey everybody, welcome to Longshot Space here in Oakland at our headquarters. We've been operating here for over 3 years now, but unfortunately, the space is becoming a little bit small. So we're going to move to a larger facility down in Alameda, right next to our test facility where our next generation accelerator currently stands at. That unlocks the capabilities for us to test at larger scales, to have more room for manufacturing, as well as more room for the engineers and the business team to expand.
There's enough room there to actually build the full-scale vehicles, maybe not for space launch, but for all of the hypersonic testing. So I'm pretty excited about that new facility.
Today we're starting the test sequence of our side injection test rig. As you can see, there's 2 pressure vessels attached to the left and right side of this test rig. Those are firing gas onto that V-tail to basically squeeze it forward. In this particular case, this is all static, so we're not having that projectile be in motion. However, we can correlate this data to our simulation data to see how much force actually gets translated into thrust.
Translate clockwise. Ready to fire.
3, 2, 1.
So what you can see here is basically a projectile model. Back here is our V-tail. So this is exactly what we're trying to test in the static test rig. We're impinging gas onto that V-tail to basically squeeze this and accelerate it forward.
So last year we had basically preliminary design for the tail. We knew the basic geometry, some of the parameters that would be important. And this year we started working on the vehicle itself. So the whole projectile that is launched from the accelerator is basically composed of 3 portions. A vehicle at the front, which has a heat shield mounted on the front of it. Then there's an inner stage, which is sort of a clamshell that joins around the vehicle and joins the vehicle to the arrow wedge. And the arrow wedge is the part that the side injectors squeeze onto to accelerate it down the barrel. The vehicle is the portion of the projectile on the front that basically detaches from the tail and then ascends through the atmosphere up to the target altitude. So if this is an orbital class system, the vehicle is the part that carries the payload all the way to orbit. Leaving the atmosphere is really hard at these types of speeds, and the specific geometry that you choose for the vehicle has a huge effect on the performance. The most common category of vehicle for this application is a waverider. This is a vehicle that is specifically designed to take advantage of those high hypersonic speeds and produce extra lift.
The purpose of why they call them waveriders is they are riding along a shock wave that they create. So when you break the sound barrier, it's not a one-time thing. You're constantly breaking the sound barrier every time there's any sort of fluctuation in your relative angle of attack while you're flying. So when doing that, it takes a lot of energy. And since we have a finite amount of energy, we're not a traditional aircraft, we're not flying with an engine. We need to find a way to take advantage of that rather than just wasting it. So waveriders do that. As we skip along the atmosphere, the reason we say that is because when you go up and up and up, and you get to a point where there's almost no atmosphere, you've got nothing to skip on, nothing to push against you. So as we come back down into thicker air or a proper atmosphere, then we generate that shock cone again, and we have more surface and more density to push off of, which allows us to kind of skip like a rock. When you skip a rock, you see it every time it hits the water, it comes back up, but it's got nothing to push off it really comparatively in the air, so then it goes down. And that's kind of exactly what we're doing.
The geometry is really important. The exact contours and shape of the vehicle defines key performance characteristics like the lift to drag ratio. And as we ramp up off the atmosphere, we want to minimize the drag and get as much lift as we can without hurting the performance of the vehicle.
On top of that, we need to be able to carry some sort of internal payload for sensors and other atmospheric data collection. We need to be sure that the shape of the vehicle will actually work. Can we handle thermal loads? A lot of these things are going to be going under extreme pressures and extreme forces and extreme heating. So I work with NATO to design the end of the projectile to accelerate to said speed, and then more importantly on my end, the actual shape of what the vehicle looks like, which is roughly where this behind me comes in. We go in here and we say we want to design something for some speed value. We can click generate and it will create our shape for us. we'll take this file as a starting point and export it to both CAD and then remeshing softwares. And then we can put that into a computational fluid dynamics simulation, which is what Anton is leading there.
The pink purple is very high temperatures, blue is low temperature. So here we can see temperature distribution on the outer mold line for a particular flight condition, and that can help our structural and thermal protection system engineers kind of understand the environments they have to engineer around and sort of requirements that their systems will have to meet.
There's a whole bunch of geometries that look really cool. So once we've got a basic geometry that works, we then have to refine it into something that is easy to build. Right now, we are still scoping out how thick of a heat shield and exactly how that's going to be manufactured, but we're pretty confident, especially for the high hypersonics, that we're going to definitely need a heat shield.
I suppose it should go without saying that live testing this is going to be a large effort, and it's not realistic to try to do that and then take the data back at this stage in the company. So being able to model and understand exactly what the aircraft is going to be capable of handling and what it's not going to be capable of handling is crucial.
With how powerful computers are nowadays, we can do a lot in that digital world and have more confidence going in when we start prototyping and testing those big systems.
So it takes this magical mix of people that are willing to work on and approach this problem from a very different way. You know, the team, when they first got together, they did a first principles engineering approach and said, what is the absolute most affordable way to get mass to Mach 25, to space velocities, escape velocities? And NATO and Mike and the folks that they built, they were willing to think about it from that perspective. You know, most rocket scientists, they want to go work on the next cool rocket, which is great, but it's not revolutionary. What NATO and the team are doing is something that's absolutely, totally revolutionary, and it's game-changing. It's going to disrupt the market. So it's exciting to be a part of that team and to watch what they're doing.
There was a paper in the 70s that discussed this, and another paper in the 80s, and another paper in the late 90s where people talked about using this technology. And I think we're the first people to actually try to implement it, though. The papers just say things like, the engineering challenges of implementing this are formidable, and things like that. So people have had this idea before, but everybody has sort of thought it wasn't really possible. So we're trying it out.
Everything that we can prove that has only ever been done on paper takes us one step further to myself and everyone else believing the big long-term dreams. So I would say I'm cautiously optimistic, but I think that's just part of the nature of my field. Just because no one's done it doesn't mean it can't be done, and the math says it should be possible, so let's go prove the math right or prove it wrong. And we'll see what happens.